Welcome back. So this is going to be my last video in the video series on looking at one-dimensional problems where I'm trying to solve the eigenvalue equation for the Hamiltonian. In all of these problems, what we've been doing is we've been trying to find out whether or not the Hamiltonian gives us a set of bound states, right? Or in some cases gives us a set of continuous states. But I apply the Hamiltonian to my wave function, and that then is an eigenvalue equation where the eigenvalue is the energy of the state. Well, today I want to focus on a subset of potentials where my potential is constant for any given region of the domain. Let me say that a better way. I can take my potential and I can write it as a piecewise function where each of the sections of my domain in that piecewise function are just a constant. And you might think that that's special, but it really covers a lot of the potentials that we've been looking at, right? The infinite square well, the finite square well, even the delta function well. All of these examples are places where for any region of the potential, right, any region of the domain, the potential is just a constant. And if I can do that, then when I look in each one of those regions, I can write down the eigenvalue equation so that it looks like the second derivative of the wave function with respect to space is just equal to, something times E minus V, or E minus V naught, right? Whatever the potential is in that region, times psi. And therefore, in looking at this, because that thing is a constant, right? And that's the thing that's important here, is that coefficient is a constant. I know that this thing is either going to give me something that looks like the shoe, if that constant is positive, or it's going to give me something that looks like the shoe at a top place, right? An unstable part of the shoe, right? In other words, my solutions are either going to be complex exponentials, right? Because it's the simple harmonic oscillator equation, or they're going to be regular exponentials because it's like falling off a cliff. And so if I have a potential that's written like this, I can write down the solutions in each one of the regions, in each one of the pieces of the domain. And to find out what the two possible independent solutions are in each one of those pieces of the domain, I just have to know the difference between my eigenvalue, the energy of the state, and the potential, which I'm calling V naught for any particular piece here. So if E minus V naught is less than 0, that is the state's energy is less than the energy of the potential in that region, then I'm going to have regular exponentials, right? That is, it's either going to decay away or it's going to exponentially grow. If my E minus V naught is positive, that is, the energy of the state is greater than the energy of the potential, well, that's when I have my solutions to the shoe. Sorry for missing those constants of that proportionality symbol. Anyway, then I have my complex exponentials, right? I have my sines and cosines. I have my wiggles, right? So if the energy of the state is less than the energy of the potential, it's not going to wiggle. If the energy of the state is greater than the energy of the potential, then it's going to wiggle. Okay? So I like to see this sort of as a picture, right? So in this case, I'm going to just choose two different regions, one where the potential is sort of low and one where the potential is sort of high. And so if the energy of my state is bigger than my potential, I know I'm going to have these two solutions that look like e to the ikx and e to the minus ikx. So e to the ikx and e to the minus ikx. And we know from studying these that a solution e to the ikx, well, that's just a eigenvalue of the momentum operator, right? It's just a state with momentum k. Well, it's a complex exponential, but it is an eigenstate of the momentum operator, and therefore we can think about it as an object that has momentum moving to the right with some, eigenvalue k, right? With some momentum k h bar. And so I'm going to write that sort of as just sort of my pictures. I'm going to write it as a squiggly line to the right to remind myself that that's a complex exponential. It's not actually squiggly, right? Because it has the constant norm, but that's just squiggles is what's going to remind me that it's something that's actually moving to the right. And then my e to the minus ikx is something that's moving to the left, right? Because there the momentum is minus kh bar. Okay, and now the general solution in that area then has to be some amount e to the ikx plus some other amount e to the minus ikx, right? Two unknown coefficients that I'm going to have to solve for, probably using some sort of boundary condition. Whereas on the right-hand side, if I have my energy less than my potential, then I only have two choices, right? Well, I guess I always have two choices. I have something that's decaying, where it goes as e to the minus, let's say, kappa times x, or it's growing, which I have e to the plus kappa times x. But because the energy of the state is really, it's less than the potential, I like to think about this as sort of the wave function can't, it can't propagate through it, right? The best it can do is sort of decay away while it's inside that potential. And I can use exactly this logic then to start to build up what my solutions might look like over a wide and complicated domain. So if I have this picture here, right, I have just a bunch of different things everywhere. I know it's complicated. And I find out, okay, well, here is going to be the energy of my state, right, given by this line. I can say, well, in this region, in region 1, the energy is less, and therefore I'm going to have to write the psi 1 as, a e to the kappa x plus b e to the minus kappa x, right, because the energy is less. Here, psi 2 is going to be a complex exponential, so can't call it a, let's call it c, e to the I kx plus d e to the minus I kx, yada, 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 all the way across, right? And once I break this up into problems, the rest is just algebra. I know. We did the finite square well. We realized that the phrase just algebra is not a very nice thing to say among friends. But I end up with this situation where I'm able to solve for these coefficients in principle if I know what the wave function looks like in each one of these regions. Okay, I'm gonna have a bunch of equations because so long as the potential is finite, I know at every single junction, right, at every single interface between two different sections, the wave function is going to be continuous and the derivative of the wave function is going to be continuous. And as I said, we use this to solve for the finite square well, right? I had a wave function that came in from the left, and it was a growing exponential. We got rid of the other term because it can't be infinite at infinity. Same thing happened on the right? So I have these two solutions that are decaying exponentials away from the well. And then when I added the complex exponentials together, I either got sines or cosines. Let me draw the sine one. Oh, no, I hated that. I should draw a cosine one, right? Forgive my artistic, but right, I can develop what these states are going to look like by adding the wiggly part in the middle, and then adding the wiggly part where it's wiggly, and then having the exponential decays where it's exponentially decaying. But what's beautiful about this is now I can use this process for all sorts of phenomena, right? So one that we look at a lot is this idea of scattering. So if I have this sort of potential where I have V1 on the left and V2 on the right, if the energy of my state even is up here, right? So this is my energy. I'm going to have complex exponentials on both sides, right? So over here, I'm going to have some particles coming in, right? So I'm going to say a e to the I k1 x, and I'm going to say k1 because that's the k corresponding to v1, and then maybe some get reflected, right? The first term are the particles moving to the right. There's this weird interface, so perhaps some are going to be moving to the left. I'll call that b e to the minus k1x. Whereas over here, I'm going to have a psi 2 that's equal to c e to the I k2x, because some of the particles are going to go through, right? The energy is big enough so that classically it's going to go over the barrier. And now I'm set up in a place where I have boundary conditions that I can match at the middle, and I can find out, well, what's the relationship between A and B, right? Or maybe better, what's the relationship between B and A, meaning how much of that is reflected, and how much is the relationship between C and A, which could give us some idea of how much of the wave got through, right? And the continuity of the wave function and its derivative at the middle are going to be the things that define for me what this scattering process looks like. Now, the one big exception to that is, of course, even if I'm doing this for, I don't know why I wrote A. Even if I'm doing this for scattering, right? I could have A e to the I kx plus B e to the minus I kx over here, and psi 2 is equal to c e to the I kx over here, I can do this for even delta function barriers or delta function wells, right? I can still do this sort of scattering problem here. But remember, whenever I have a delta function, that's the one exception to when the wave function is the derivative of the wave function is discontinuous. And so in order to get the condition to tell me how to match the derivative of the wave function across this interface, I have to integrate the eigenvalue equation in order to find out what the difference in slope is between the left-hand side and the right-hand side of the barrier. And that's just something to keep in mind. But one of the sort of neatest things that come out of this whole analysis is the idea of quantum tunneling, right? And so let me start with the finite square well as we knew it, and let me just draw the ground state. Okay, so that's the one that comes up, it goes down, and then in the middle it just has a bump in it. Okay, well, if I take this idea of being piecewise defined and I say, okay, well, I'm gonna cut the potential over here. I'm going to make it so that it drops back down, right? So that is that the right-hand side of my potential now has, it's not going on forever. Well, I can see, at least conceptually, that part of my wave function, which was exponentially decaying, now finds itself outside of the potential, right? Where it's no longer going to be a damped exponential. It's now going to relive its life as a complex exponential. It's gonna recreate itself as a particle that's free to propagate, that has momentum. And so what happens over here is that my wave function no longer looks like a decaying exponential. Rather, it looks like a free particle over there. And that's what we mean by tunneling, right? And that the wave function can still permeate through finite barriers over some distance, right? Because they have because the solution to the eigenvalue equation there is a decaying exponential. It doesn't end where the barrier ends classically. And so if it leaks a little bit out, it can leak a little bit across a wall, and that allows a little bit to propagate then as a free particle on the other side. Now, the math in this problem is a little bit trickier than I say here, because of course we have to worry about normalization and what happens and when do I turn it on. But anyway, the point is that this is the perfect graphical picture for understanding what we could do with tunneling if we think we have something trapped, but the barriers to either side aren't sufficiently large that something's able to leak across. Okay. Anyway, I hope I've introduced a nice, fun, large set of problems that we can do with the tools that we already have. So if your potential can be written as a piecewise set of constant potentials, then you can solve the eigenvalue equation in each one of those regions independently. And as long as you remember that the wave function is always continuous, and the wave function is the derivative of the wave function is almost always continuous, except if it's a delta function, then you can write down all those matching conditions, algebra, and you can find out what the wave functions look like. All right, good luck.